To continue now, we have to Mauricio Sepúlveda introduce the Professor Ivan Moyano. You can start, Mauricio.
Okay, thank you for the invitation and the possibility to present Professor Ivan Moyano. Ivan Moyano is a young and Spanish mathematician. He's in this moment in the University of Côte d'Azur in Nice, and his presentation is about the quantitative uncertainty principles in control theory. Please, Professor Ivan Moyano, you can start.
Thank you very much, Mauricio, for this nice presentation, and especially for insisting on the fact that I'm young. It's something I have to remind to myself from time to time. Thanks a lot to all the organizers, and especially to Diego and Juan Limaco for inviting me. Well, it's always a responsibility to give a talk after Jean-Michel Coron for many reasons. But one is because, well, he's certainly interested in non-linearities and non-linear systems. And now I'm giving a talk which is fully linear. So typically in the linear regime, well, in order to justify why you're doing linear stuff, you need to say something really, really precise about the problems at hand. So this is completely linear. And well, the main say ingredient or motivation of my talk is control theory, of course, especially controllability of the heat equation and how we understand it now after some time, so more than 20 years, and how it relates to the classical uncertainty principle and the possible extensions or different interpretations of the uncertainty principle. Now, what is the classical uncertainty principle, at least as I understand it? Now, well, it was discovered in 1927 by Heisenberg that in the quantum mechanics formalism, position and momenta do not commute. There is a huge restriction compared to the Newtonian or classical physics. Now, how can we understand this in mathematical terms? Well, the classical uncertainty principle can be understood as a statement about the Fourier transform. Now, what do I mean by this? So if we consider a function, say in here, a function that might be complex valued from RD to C, and we assume that this function is, well, represents, say, a wave function in quantum mechanics, so it's simply of L2 norm equals 1, we can ask ourselves the following question: how localized can be the Fourier transform of psi and psi itself? Now, a quantitative version of that is what leads us to the uncertainty principle. Now, so if we define the mean in frequency here, which is the Fourier transform of psi to the square times psi, which is the frequency variable, and then we integrate with respect to RD is a sort of expectation, right? If we see this as a random variable, we call this guy, say, psi bar, and we take a look at the quadratic deviation around this mean in frequency. Now that would represent how localized the Fourier transform is in frequency. So if this is the graph of the Fourier transform, say we can take a look at how localized it is in terms of its support. Now, if we do the same with the function psi in space, this function here, and multiply x and then integrate by with respect to x, we give the mean in space, and then we can do the same and define the quadratic deviation in space, which is this quantity. So that should gives us some information about how concentrated it is psi in terms of the space variable. So that would be something like this in terms of the graph. So this is telling us how concentrated it is in support. Now, what happens is that we can make a simple computation by, say, integration by parts and nothing else, and we get this inequality. So the product of the quadratic deviation, when you take the square roots, is always bounded below, and this bound is strict unless the function psi is Gaussian. Now, this is very classical and somehow tell us that a function cannot be localized both in frequency and in space at the same time without being zero almost everywhere. Now, the question is, this being the case, what can we say about it when we put ourselves some extra, say, hypothesis? So can we optimize the localization conditions on space of frequency? It cannot be compactly supported, but how can it be? It could be larger. So what if, for example, the supporting frequency is simply a ball? So we give ourselves function whose Fourier transform is compactly supported, then how small can be the support in space? This would be a natural question. Well, this question has been answered in many circumstances, and now is called, at least in the whole Euclidean space, Logvinenko. Let me write it. Sereda inequalities. Sorry. Inequalities, or in Logvinenko's Sereda conditions. So this comes from the 70s, and these two guys were two Soviet mathematicians working on function analysis, and they were trying to find some conditions on the space such that the restriction of the Fourier transform gives an equivalent norm to the L2 norm. So that's essentially this. Now, the Logvinenko-Sereda condition is the following. Now, remind you, but just recall that we are assuming that the Fourier transform is reported in a ball. The support of the function in space cannot be too small. It can be, it has to be spread out in the whole of RD, but we can give some fine condition, which is the Logvinenko-Sereda condition. Now, what is this? It's a quantitative thickness condition, which works as follows. So imagine that we can divide the whole space RD in cubes of length r. So that would be one of those cube of length r. So this quantity is r. Now, the Logvinenko-Sereda condition is the following. So if we pick some omega in RD, which is a measurable set, we want this omega to be not too small in each of the cubes. So in each of the cubes, we must have some part of, say, a chunk of omega in such a way the infimum of the measure of omega intersected with all of the cubes is at least bounded by some parameter gamma, and times r to the power of d, r being the length. Now, this means that omega doesn't need to be open. The only The only condition is for omega to be, say, in measure, not too small. So it can be very small. So each, say, connected component of omega can be very small, but the sum of the measures of the total measure in each of the cubes has to be bounded below by some uniform parameter. Now, in this situation, Logvinenko and Seminario found the following inequality, this one. Now, it was in the work of Logvinenko-Seminario without an estimation on the constant. So let me put for a while, let me put simply some constant. So the thing is that under this condition, we can say that there exists some constant, possibly depending on lambda, such that the L2 norm of F is bounded by this constant depending on lambda times the restriction of the L2 norm of F on omega, as long as omega is a thick set and the support of the Fourier transform of F is in the ball of radius lambda. Right? So that's the original Logvinenko-Seminario inequality. Now, of course, this constant depends on lambda, and a natural question would be how? How exactly? And this is exactly what Kovrishkin found. The dependence has to be exponential with respect to lambda. So let me rephrase the result again. Assume we have omega thick set with respect to those parameters. R is the length of the cube. Gamma is the uniform bound below. Then there exists some constant such that for any lambda and for any function such that the Fourier transform is compactly supported in the say the ball of radius lambda, the L2 norm of F can be controlled by the restriction to omega times this constant times exponential, some possibly other constant times lambda. So the dependence with respect to lambda is exponential. So that's Kovrishkin's quantitative result. Now, just a question, when did I start and how much time do I have? Just to keep in mind.
I don't know. You can continue. No problem.
No problem. Right. Well, thank you. That's very kind. No, I was asking this because I'd like to present just the element of the proof of Kovrishkin results, so that you can have a taste of it, a bit of the flavor of this kind of oh goodness, sorry about that. Yeah, yeah, the flavor of these business. Now, just a sketch of the proof. Now, this follows the lines of the work by Kovrishkin. It's a work from the 2000s, and I recall that the goal is to prove that we can control some well, let me do it in one dimension, just as Kovrishkin himself. We want to control this thing in terms of the restriction on omega, assuming that omega is thick. So say assuming that for every, say, interval of length, just to simplify, let us put 1, this is bounded by some gamma, right? Now, the what we expect is something of this kind, as long as the support of the Fourier transform is in this thing, or bounded, sorry. Now, the elements are the following. So first, there is, say, a reduction based on harmonic analysis decomposition in cubes. So you decompose the whole space in cubes. You call some of them good and some of them bad according to the fact that the good ones satisfy some nice property and the bad don't. Just like in the Calderon-Zygmunt decomposition, for example, and Whitney decomposition, many of them. Now, in the one-dimensional case, what we do is, well, we take some of the intervals in R, and we say that I is good if essentially the Bernstein inequality works in I. Now, what is the Bernstein inequality? Well, it is a property which is very useful for when one deals with function whose Fourier transform is compactly supported, just as like in Littlewood-Paley theory, for example. Now, the Bernstein theory, the Bernstein inequality says that any derivative of f to the power of p, I'm assuming that the Fourier transform is compactly supported, can be bounded by f to the power of p dx. But this has to be global. So it has to be true in the whole space. Now, the thing here is some quantitative, say, constant with respect to lambda and alpha and p. So we say that I is good if the Bernstein inequality works in I, say something like this. Sorry, this is lambda, right? Okay. So we have a sort of local Bernstein inequality, and we add some extra constant. Now, why do we do this? Because by just selecting the good ones, we can prove that the bad ones don't give us anything. So after some work, just pushing the local Bernstein inequality, one can prove that the whole contribution of the integral over R is given by the union of the good cubes. Now, this is something that uses the fact that the support of the Fourier transform is bounded by lambda. But what about, say, the unique continuation? Now, there is a second thing, which is the unique continuation for, say, holomorphic functions. That is the second ingredient. Now, thanks to this local Bernstein inequality, Kovrishkin finds that it is possible to bound every derivative of f in good cube by let me see, some constant depending on the usual suspects and times the LP norm. Well, now p is equal to 2. That's not a big thing. And this is very interesting because when we use the fact that, as Jean-Michel mentioned before, Paley-Wiener tells us that any function whose Fourier transform is compactly supported admits a holomorphic extension. That is very nice, but it's actually very straightforward. What we need, and this is where Paley-Wiener is very useful, we need some extra estimates. Now, these estimates come from here, because what we have to do is to bound derivatives in, say, in the Taylor expansion. So now we can bound these things. And this is essentially, say, some exponential in lambda times FLP. Now, as f is a holomorphic function, we can, say, extend it, say, in a neighborhood, a complex neighborhood of I, say, we have a control on the Taylor series, and essentially we can combine all the pieces and get some local estimate of this kind. So if I is good, we have this. And as I said, this puts together some holomorphic unique continuation plus Bernstein inequalities, which are local now because they are chosen to be good. Now, how as all this integral is controlled by the union of the good cubes, the result follows. So the control we get, or the effect we get, is exponential in lambda, just as expected. And of course, these constants depend on gamma, r, and so on, but they don't depend on lambda anymore. So the dependence is exponential of a constant times lambda sharp. Okay, is there any? If there are any questions, you can don't hesitate to interrupt. Okay, so that would be the say the Euclidean case, in which Koryshkin obtains these quantitative results, very nice results, but it uses the fact that the Laplacian in RD is a constant coefficient operator, so it's diagonalized by the Fourier transform, by the classical one. So there is this very nice duality between the Laplacian operator and the Fourier transform. Now, what happens if we deal with variable coefficient operator, something like, for example, Schrödinger operators of the most classical kind, a Laplacian plus some potential. Now, this potential, if it depends on the space, as usual, changes everything. The whole picture changes, because now the Fourier transform cannot be used as just as in the case of the Laplacian, because it doesn't diagonalize the operator anymore. Now, what then diagonalize this operator? Well, if we look at it, we see Laplacian depending on the metric, so it is a variable coefficient operator, and we see a potential. Now, what we know is how to describe the spectrum of the operator. So we know how to deal with these kind of operators in terms of the spectral resolution. And what happens? What happens is the following. So if I consider, just as here, V, a potential, which is, sorry, I didn't mention, is a real potential, real valid potential, decaying polynomially at infinity. And G is, well, of course, variable coefficient, but it is an asymptotically flat metric. So it's at infinity, we can think of it as just as the Euclidean metric. So it's just the identity. But it can be, it can depend on the space from point to point, at least in some part of RD. So it is not a constant coefficient operator. Now, what happens under this hypothesis? Well, what happens is that we can describe the spectrum. So there would be, this would be the complex. This operator is self-adjoint, so its spectrum is real. It may have some continuous spectrum, and it actually does. So this part of the spectrum is continuous. Oops, sorry. But by the action of this V and this metric G, it can create some eigenvalues which are discrete. So it would be, say, the discrete bar would be the quantum world, and the continuous bar would be the classically forbidden, and so on. Or the other way around, probably the other way around. Right. So what happens is that if this potential is what people call in scattering theory long-range perturbation, so it has to do with the decay we expect, this discrete part of the spectrum can accumulate around 0. So there is no chance we can say something about the Fourier transform. It is not relevant anymore. What is relevant, though, is the spectral projections. So the spectral projectors allows us to say select just part of the spectrum up to some energy level, say lambda. So for some lambda given, we define these spectral projector. Right, so we are just truncate the spectrum at some energy level and just took what is to the left of it. So for another lambda, we would take, well, part is discrete, part is continuous. It doesn't matter. We can deal with it using functional calculus. The only thing is that we don't know exactly how these spectral projector writes. Is in general it should be a pseudo differential operator if you want to write it down, but we don't need that. The thing is that it's not explicit. It doesn't matter. Now, what we can say, this is a work with Gilles Lebeau from some time ago, is the following. So if under this hypothesis on the polynomial decay of the potential and the Laplacian, or the metric, we can define the spectral projectors. And if furthermore we assume that these metric G and these potential V are analytic, and this is important for us, and have some holomorphic extension on a set which is a tubular neighborhood of RD, of width, say, constantly A. And if we assume that omega is a thick set in RD, so omega would be there, then we can say essentially the same thing as in Kovriskin case, but for a much more general operator, which is a variable, which is a variable coefficient operators, and which is not explicit. So what we say is the following: there exist two constants, of course, depending on omega, depending on the coefficients, such that for any lambda r, now we take any level of energy, because we have a discrete spectrum which is possibly negative, so we need to consider some lambda negative as well. And every f in L2, we have the spectral projection in L2 in the whole space can be bounded by the restriction of the spectral projection to this thick set omega, but the price to pay is this exponential with respect to lambda. Now, as we have a negative part of the spectrum, we need to use this convention, saying that well, the square root of lambda would be the usual square root if lambda is positive, and I times the square root of lambda in absolute value if lambda is negative. So this means that actually this loss only affects really the lambda positive, because the lambda negative have here a complex unit here, and therefore the modulus of exponential I something will have modulus 1. So the result is very sharp on the discrete part of the spectrum. It is exactly as expected in the continuous part, but this behavior with respect to the discrete part of the spectrum is, say, unexpected or a bit new. Right. Okay, so perhaps I can tell you just something about the proof just in one slide, and want to bother you much about it. Now, the idea is the following. So I think it's a nice picture though. So we work in RD, and we see RD as part of CD. So we work in the complex, say in the complex plane or the complex space, and we have to consider RD as, say, a small fiber in a neighborhood of, say, width A. So this is where we are working, right? So that would be some of those neighborhoods. Now, within RD, we have our omega, which is assumed to be thick, just as before. So it is spread out sufficiently, right? As I mentioned before. And what happens now is that in order to get, say, some function f whose spectral projector is compactly supported, or not compactly supported, but goes up to level lambda, right? We can have some continuous part and some other. This spectrum is here. We need to do something, and what we do is to use an interpolation inequality for holomorphic function. Remember that unique continuation in the case of holomorphic function is fantastic. So the interpolation would be the following. Now the L2 norm of f in R is going to be bounded by some constant times omega times, let me write two integrals to say that in here we have the integral on the tubular neighborhood. So this is true for some constants. Alpha is between 0 and 1, and this is true as long as f is holomorphic in UA. And of course, well, the usual norm makes sense. So it's L2 and so on. So this is a sort of a three circle or three sphere or three ball theorem. But having some global aspect, because this RD is global, UA is global, so we can patch together a bunch of local estimates in order to get this. Now this is the core of the argument, and what we need is to say that, okay, that's very nice, but we need to bound this thing by something of this kind, right? In order to, divide it by it and get the spectral inequality. So in doing so, we need to use some holomorphic mumble jumble, some holomorphic extensions that actually use the Poisson kernel. Now, this sounds a bit weird, but if you look at the Poisson kernel as the solution to some elliptic equation, well, it's essentially the operator with symbol as psi, something like this. So so that would be the solution to a problem in the Hull space that gives you the Poisson kernel that you can write explicitly. And in terms of the Fourier transform, is just the exponential of S psi. So this exponential of S psi is exactly what appears here, right? So this is exactly what gives us the exponential of C lambda. Now, where this idea come from? Where does this idea come from? Well, I guess it's natural at some point, but only when you know the usual FBI approach in microlocal analysis, because otherwise it is not natural at all, or the works by Boutet de Monvel in the 70s about some, there's a famous theorem of the extension of the holomorphic extension of the spectral family, or for the Laplacian analytic manifold. So recently, Lebeau gave new proof of Boutet-Monvel theorem using an FBI approach, and this FBI approach is exactly what is behind the use of the Poisson kernel. And in general terms, I'd say that the FBI approaches you can find in many places, like Zworsky's book, is say a different way to quantize, or a different quantization than the usual one associated to pseudo differential operator. But the ideas behind them are very similar. Now, this is what is behind, and uses a lot of analyticity and holomorphic ideas. But we realized after that they are not necessary. So they're just sufficient, and they are nice to work with. They give you a lot of information, but they are not at all necessary. Now, what can we do after that? Well, we can take a look at the compact case just to tell you the end of the story. What happens in the compact case? Well, in here well, there's no such uncertainty principle. What is concentration of eigenfunctions. The idea is the following. So if we consider a compact Riemannian manifold, just like this, we can define a spectral family, and this spectral family EK is associated to a sequence of eigenvalues lambda k that go to infinity, and they are discrete. So in here, the spectrum is always discrete as long as the manifold is Riemannian. Now, if the manifold has a boundary, we can prescribe either Dirichlet or Neumann conditions, and that's it. You can do plenty of stuff with them. Fourier series, plenty of things. Now the question is, if we are given some omega, say, on the manifold, say is an open set on the manifold M, what can we say about the concentration of the EKs on the particular omega? Can they concentrate in some norm or not, and if they do, what is the loss in terms of the loss of orthogonality? What is the quantitative constant in the unique continuation principle if they concentrate enough, and so on. So that would be the question: how much the EK concentrates in a given omega. Right. When I write here the Laplace Beltrami operator here, well, I mean it as just the usual definition you can find in any book about differential geometry. But the thing is, in terms of I mean, for analytic people, it is a variable coefficient operator whose coefficient depend on the metric. So the regularity of the operator is the same regularity as the metric, as the one of the metric, more or less, or they are connected. And by regularity of a manifold, we mean a manifold whose metric is of a certain regularity, analytic or smooth, or C1, for example. And that means that the transition maps or the local charts have at least the same regularity. Now, this is important because I will use it in a minute. Right. So the classical result in this business is the one due to Jerison and Lebeau in the 90s, which is the following. So if M is smooth, so say for a metric which is smooth C infinity, right? So that would be a C infinity operator, but actually it works down to C1, more or less. And if omega is an open set in M, then we have a spectral inequality which is the same thing or analogous to the one in the Euclidean case. So we can say that there exists a constant that depends on omega, of course, such that for any lambda, the L2 norm of any function on M, EK, remember, is Hilbert basis, so CK are just a number of coefficients that are given, is bounded in terms of the norm of the same function on omega, the concentration, right? Times some constant times constant lambda. Now, this is just a notation. If I put here lambda square, which is the case where psi as the frequency, say, well, the Laplacian is, the symbol of the Laplacian is psi square. Now the symbol, say, of the Laplacian should be lambda k square, and in that case, we have C0 lambda. If I say that the symbol of the Laplacian is simply lambda k, what we have is square root of lambda. So it's just a matter of notation. It's as simple as that. But the numerology is exactly the same. So if we put lambda k square, we have a constant times lambda, and the loss is exponential. Now, this is true for any given coefficient, for any coefficient which are complex, because it's exactly what we expect. This is, say, the spectral projection of a function, and the analogy is complete. Now, this theorem is a consequence of the use of Kahneman estimates. I haven't mentioned them, but we actually use them with Lebeau in the result I presented before to get the interpolation inequality, and they are ubiquitous in this business. Right. Now, we can say something more about this compact case. I mentioned before that we could get rid of the hypothesis of analyticity as in my paper with Lebor, which we can do at last, that's true, and we can simply consider some Laplacians, just like here, whose coefficients are C1 intersection W to infinity. So two derivatives are bounded, and that's all we need. So that's a lot less than the analytic case that I mentioned before. Now, the situation is the same. We have a Riemannian manifold, but now the regularity of the metric is less than, well, it's essentially that. The spectral family, of course, is still well defined. If we have a boundary, we prescribe either Dirichlet or Neumann condition, and the regularity we need on the manifolds are this. Now, the thing is that using some new tools from Logunov and Malinikova in the study of the Gauss conjecture, we can give some more precise spectral inequalities, which are valid not only for open sets, but for measurable sets, and even for zero measure sets, negligible sets, whose house of content is not too small. So what we get is the following. Now, so under these circumstances, we prove that there exists some delta such that if we have a measurable set with non-zero measure, or a measurable set possibly with measure 0, but such that the house of content is not too small, then we have an L infinity L1 spectral inequality. But I have to say here that as I put here lambda k, I should put square root, and the same with the other. If we put lambda square, we've got lambda. The same with L infinity, L infinity. Of course, when E2 is not has possibly measure 0, we cannot consider the integral. So the only hope is to consider the supremum. Right. So what it means to be small. So in these circumstances, E well, essentially can be covered by balls of a certain radius, and the house of content would be the infimum of the sum of those radius. So that gives us a measure of how small set should be. So this works, for example, for fractal sets, these kind of things, or the trajectory of the Brownian motion could be a set whose house or content is not too small. So not necessarily open sets or measurable sets with positive measure. In terms of the controllability, because for those of you who are interested in controllability, that means that we can obtain observability inequalities for the heat equation, where the controls are very rough, so they are typically measures. So that would give an impression of some kind of impulsional control, right? So the control should be supported in some, for example, in the 2D case, it cannot be supported in a curve, but it could be supported in something slightly larger than a curve. So it looks like an impulsional control. So this is the kind of controllability results we get with Nicolas Burck. Now, just to finish, I'll just give just one idea of the proof. Is just that. So we first work on the say the case without boundary. Now, if we don't have boundary, we know that there is, well, at least some say small omega, as it is compact, well, such that the house of content is not too small. So we can use a partition of unity and essentially work on some of the neighborhoods, say, in which this is true. Now, from here we can go down and work on local charts. Say we can U and some neighborhood of V. We have a neighborhood here, so it's the usual work on local charts. And what we do next is to use the localization procedure, say, that we know is true thanks to Jerison-Lebeau. So we actually work with their inequality, or we use their inequality to get ours, right? And then we use we go back to local charts. So this is Jerison and Lebeau. As I said, it works in C1. And then what we do down there is to use well, the usual unique continuation argument. But now what we use, and this is very important, is that would be omega. That would be the image of omega is this Logunov and Marinikova result, which is again an interpolation inequality. So is something of this kind. So that would be a three circle again for some compact K, some small set omega, and some big omega, which is larger. Now we use this quantitative propagation of smallness and some elliptic regularity as well, and we get what we want. And we can deal with this kind of very small sets because they know, they learn, or they understood how to do it. They were interested in Yau's conjecture, which essentially deals with the understanding of the novel set, or how large they are with respect to the lambda case. And if mu is the house of measure, Yau's conjecture states that lambda k, well, the dependence should be square root. So they got very, very nice and profound and deep results recently, thanks to which we were able to extend what we know about spectral inequalities, and in particular deal with these very small sets. So this comes from this propagation of smallness business, which I strongly recommend you to take a look at, because it's a mathematical jewel. It's fantastic work. I mean, their work. I mean, so should be everything, and I thank you for your attention and your patience. So thank you very much.
Okay, thank you very much, Ivan, for your presentation. Now, some question about there is some question.
Okay. I would like to make two questions. Before all, thank you very much for your talk and for your participation in the seminar. And the first question is it possible to have a similar result with boundary observation? I mean,
yes, I didn't. Yes, I was running out of time. I thought I had to finish. Yeah, so that's what I wrote one, because the second step is to tackle the case of the boundary. So as I wrote here, we put Dirichlet or Neumann. And the idea is that we know that without boundary, that's okay, that's fine. So that's not surprising. But some new idea perhaps in the paper is that what we do is to use something called the double manifold that comes from, well, in particular from dispersive equation, and has been applied in dispersive equation. So the idea is the following. So if the manifold has a boundary, what we do is to create a new manifold, which is the double manifold, by, let me write it clearly. Say by gluing the two boundaries. So what we do is to create two copies of the manifold, and then we glue the boundary. So the double manifold would be, say, well, topologically would be a sphere, something like that, in my picture. And now this thing doesn't have a boundary. But, well, it sounds a bit magical, but of course there's a big problem to define well, what happens here to define a chart, say, which is valid in the overlapping part, and this works under this regularity, and essentially only in the case of Dirichlet or Neumann boundary conditions, because we can say, for example, for the Dirichlet boundary condition, we can define if E is one of the eigenfunctions in this +1, say in one of the copies, it would it is the function itself. In -1, we need to put -E, and it's exactly the symmetry that makes it work, the procedure. And for the Neumann boundary condition, it would be E and +E. So we can extend the spectral family on one of the copies to the double manifold. But of course, there's a lot of work to do to, oops, sorry. There's a lot of work to do to prove that we actually have a chart there. This is difficult. So yeah, so it works in the case of domain with a boundary, but Dirichlet and Neumann only because of this symmetry. Well, I don't know if it works in the rest of them, but it works in the case of Dirichlet Neumann for sure. I don't know if I have answered.
I'm not sure, because I was asking for the inequality that you got with Burke.
Yeah.
If you are able to get something similar with an observation on the right-hand side, just on the boundary.
No. Sorry. No, I misunderstood. No, I think that this kind of, so something like sorry, Enrique, I think I misunderstood. So something like this, right? So So this would be M, and that would be the boundary of M, right?
Well, maybe some derivatives of ek there on the right hand side, something like the normal derivative or something like this.
Yeah. Well, this specifically this.
No. I mean, on the right hand side, you are not going to put the same thing that in the left hand side. You should put something like the normal derivative of the sum.
Yeah, because so this case is clearly false. For example, for the Dirichlet case, right? But so if we put something like this.
So I don't. Well, I don't know if it's true or not.
I think that
this was my question.
In general, I think it is. In general, I think it is not. There are some. I think there are counterexamples. I think there are counterexamples. I think in the case of the disk, I think, but I'm not entirely sure. But I don't think it's true. No, in general.
In 1D, it's false. In 1D, it's false. You cannot...
Okay, 1D is yeah. Okay, 1D is false.
But I think that in spite of this, I think that Lebor-Robiano proved something on the boundary controllability. I don't know if taking the mean in time or something like this, or the you have to introduce time maybe to get a similar inequality. But anyway, this was my question. So
that's interesting. Sorry, I think I misunderstood the question first. Okay, no, I see that's interesting. Yeah, I should read Lebor-Robiano's paper again.
Okay, my second question is if what you have said is also possible to repeat in the case of the fractional Laplacian. So, do you really need that to have a second order partial derivative operator, or you can have a partial a fractional Laplacian there?
Well, you mean, so if I replace the Laplacian and I put some fractional Laplacian like this, right?
Yeah.
Well, so in the compact case, well, if I'm not saying, if I'm not completely wrong, well, the eigenvalues would be essentially well the same, with the power would be different. So the spectral inequality, I mean, would be the same functions. So the spectral inequality would be the same. What happens is that, what I think happens is, in terms of controllability, in order to compensate the high frequencies with the low frequencies, well, the dissipation associated to this thing is worse and worse. So there might be this range, which is good. So I think that should have controllability, and in here, which is possibly bad.
Yeah.
But this is, I think this is probably known, but I fail to see how to get, so if we replace in here the Well, I think we have something like this. So
Yeah.
the spectral family will be the same. So yeah, I don't know what is reasonable in that case, honestly. No, I don't know. Sorry. No.
No, but I think this is reasonable to get something similar, no? So, no, I don't,
Yeah, definitely. It should be.
instead
Yeah.
of d lambda, you get something like d lambda to the power lower than 1.
Well, the same. Yeah, the same. The same thing. Yeah, it should. Yeah, should be something like that. I mean, I would expect something like that. Yeah.
Yeah.
So if you put, for example, in the case sigma equal 1/2, then you should get lambda 1/2. Yeah, I would expect that. Yeah. But
Okay.
yeah, I would expect that. Yeah.
Thank you very much.
Okay, thank you, Enrique, for your question. Thank you, Ivan. There is another questions. No. Then we thanks again the presentation of Ivan, and with that we close the seminar, the presentation. Thank you very much.
Thank you, Mauricio. Thank you a lot, Professor Ivan Moyano, for your nice talk.